Actually, this is joint work with my supervisor, Christian Engwer, and former colleague Niels Dreyer. So I would like to start with a small motivation. So all our computations we did were done on an Intel Skylake processor. So if you look at their webpage, it says it has an advertised peak performance of 1024 megaflops per second. Yeah, with 20 cores, this means on a single core you will get 51.2 gigaflops per second. Then there is advanced vector extensions and fuse multiply add. So if you do not use fuse multiply add, this further reduces to 25 gigaflops per second. And since it has 8 SIMD units, if you don't use those, it drops to 3 gigaflops per second. So this means classic non-parallel code will be bound by 3.2 gigaflops per second. So you will lose more than 99% of performance. So maybe we should do something there. So our idea on how to tackle this is we want to increase the arithmetic intensity and enable the vectorization. But to enable vectorization, we need some special structure. So this is not that easy. What we could do is we could vectorize over multiple problems. So there are many applications that require solves for many right-hand sides. For example, multi-scale FEM or optimization, some certain inverse problems. What they have in common is you have to solve a linear system for multiple right-hand sides. And such systems can be written as a matrix equation. So what we could do is, instead of solving multiple systems, we solve one matrix equation and solve this using vectorized solvers. So there are some vectorized solvers, and our choice were block Krylov methods. So Niels Dreyer did some work on this. So that's why we choose this. And we just leave this here. So there is work done, but we won't go in detail here. But how can we do this? How can we formulate a matrix equation for time-dependent problems? Might not be that easy. So what we consider is a semi-discrete problem after discretizing in space with finite elements. So we have some mass matrix and right-hand side function f that is possibly nonlinear. And in the linear case, we can replace the f by stiffness matrix and a right-hand side vector b. And our idea is just reformulate this problem into a space-time problem using some very basic parallel time ideas, and then consider multiple time steps or even Runge-Kutta stages at once, and then formulate a matrix equation for this resulting system and solve this system using vectorized solvers. But what I want to point out is, in contrast to the traditional parallel time paradigm where usually you choose large time steps, very many time steps in parallel, we aim for no level performance. So we want to vectorize over the time steps, so we can't choose 1,000 time steps, but we will choose smaller time steps. And then we want to enable the instruction level parallelism. So what are time integrators we consider in this talk? We will focus on stiffly accurate diagonally implicit Runge-Kutta methods. So stages of this method we denote by y with discrete time points t, and it just reads as a basic or standard Runge-Kutta method with only one major difference. If you look at the last line here, usually you have to do some linear combination of stages, but we choose stiffly accurate methods, and in that case, the last stage will just be the next approximation for the time step. Okay, and in the linear case, we can replace the f again by stiffness matrix and right-hand side vector b. So let's recall the Butcher table. For diagonally implicit Runge-Kutta methods, the matrix will be lower triangular. And for stiffly accurate methods, the BIs will just be the last row of the matrix. So, and this is the reason why the last stage is the approximation for is exactly the next time step. Some examples, very basic implicit Euler. or Craig-Nicholson trapezoidal rule. These are the two methods we will focus on. We can formulate a space-time system or an all-at-once system for the system of equations for the stages. So we consider m stages in parallel, and using the Kronecker product, this reads, well, we have seen this today a few times already. And all the stages are stored in the matrix Y, and B stores on the right-hand side vectors. And now we have some time-stepping matrices, A1 and A2. These depend on the method we choose, and they're closely related to the Butcher tableau. So A1 will just be a scaled identity matrix. A2 will be the matrix from the Butcher tableau, and B0 will contain all couplings to the previous time step. So it might happen that our diagonally implicit Runge-Kutta method is somehow special. There can be an explicit first stage. So in that case, we don't have to compute anything for this stage, and we can directly see it's just the solution from the last time step. So we don't want to compute anything, and we can move everything to the right-hand side. So we can show this for the Craig-Nicholson method, because the first entry is 0. This is a space-time system for a Craig-Nicholson method for the two stages. Okay, and in the first line, you can see for the first stage, you don't have to compute anything. So what we do is move everything to the right-hand side and eliminate this first line. But still, the second stage will couple to the stage we eliminated. So there are some additional terms on the right-hand side. Let's see here. If you look at the structure, it's just the same as before. Only these additional terms in B0. So we can leave everything as we have it. But now we have only one time step. So we want to consider multiple time steps where each time step can consider of multiple stages. So how can we do this? We have seen our time stepping matrices. We can just stack them together and build block diagonal matrices. So A1 will always be this identity, scaled identity, and A2, the block diagonal matrix where every diagonal block is the Butcher matrix. And B0 contain the entry, the couplings to the first time step. Now it also contains the couplings to all previous time steps. But those time steps are unknown, so they should be part of the left-hand side. Oh, I forgot to say that if we eliminated an explicit stage in before, you will get these additional entries in B0. So all time steps in the B0 actually are the last stage from a time step before. So we can move them to the left-hand side in the A1 matrix by just adding -1 entries. And then they are removed from the B0 matrix. And if we eliminated an explicit stage before, the same will happen in the other matrix. So now we have everything together, and we can formulate the matrix equation. And we do this for the Craig-Nicholson method. So what we consider is we eliminate the first stage and then consider multiple time steps at once. So this will be the space-time system. And this exactly looks like what we've seen before. But to vectorize over the time steps, this is not enough structure. So we need a matrix equation. So left-hand side operator has to be the same for all stages. But this is not the case until now. So what is our idea? Our idea is to apply a splitting approach and move all off-diagonal blocks from the left-hand side to the right-hand side. So now we have on the left-hand side the block diagonal matrix, and every stage has the same left-hand side operator. So this has an equivalent formulation as a matrix equation. So this is what you can see here. That's written in short. And the equivalent formulation is a matrix equation we had. You can see it in blue. The operator on the left-hand side was just 1 over tau times mass matrix plus 1/2 times stiffness matrix, and the terms on the right-hand side. But due to the splitting we make, the right-hand side of this matrix equation now depends on the solution. So we cannot solve this directly, but we have to use a fixed an iterative method, like a fixed point iteration. And in the fixed point iteration, we can solve this matrix equation by a vectorized solver block Krylov method. So far, we only considered linear problems for the formulation of the matrix equation. But of course, this can be extended to nonlinear problems. But the main difference is only the stiffness matrix K, the differ between the stages, since we use different linearizations. So what changes is the system for the parallel stages looks a little bit different, as we've seen before today. And again, as before, we can apply the splitting approach, move off-diagonal parts to the right-hand side, get the same operator on the left-hand side. But this is not enough since the stiffness matrices differ. So we need some additional splitting on this K. What is our idea? We can use approximate Jacobians for the stages. So what we could do is average over all Jacobians and use an average Jacobian for the stages. But our idea was just use the Jacobian of the first stage as an approximate for every other stage. So what we assume is divide the stiffness matrix as this stiffness matrix from the first stage plus some correction. And then we can move this correction to the right-hand side. So this means we just use the stiffness matrix of the first stage for all other stages. And then the left-hand side operator is the same for all stages, and we can formulate the matrix equation. And then we have the Newton solver in an outer loop, and fuse this with the inner fixed point iteration where we use our block Krylov method. So since we use the Jacobian from the first stage, we will perform an exact Newton iteration for this stage, an inexact Newton for the other stages. So this is why what we expect is first stage we converge the fastest. So we won't wait until all stages converge, but we employ what we call pipelining mechanism. Once the first stage converged, we will shift stages, and the first stage is shifted out, and second stage becomes first. And this is what we call a pipelining mechanism. We implemented a prototype of this approach in Dune. So the implementation relies on the SIMD interface of the C++ framework Dune. So what should the SIMD type data type be? It should behave like scalar number types, like double, float, or even SCD complex. And Dune actually provides such an implementation that is based on explicit loops and relies on compiler optimization. And that is the loop SIMD type. It's just an SCD array, and it implements the SIMD interface by overloading all arithmetic operations. For example, the operator plus. You can see it just lets the compiler vectorize this loop. So when Boolean operators now will return a bool vector, so we have some generalizations of bool in this build of bit set, like SIMD all true, any true, and you can also have a replacement of the ternary operator, SIMD count. So this SIMD type we want to use in the solver, like our block Krylov method, like block CG. So what we need is we need a vector type that represents the block vector space R to the n times S, and a spatial dimension, and S are the number of time steps we consider. So what is our approach? We just use the SIMD type we defined as a field type in a Dune block vector. So this means we just consider a single vector where each vector entry now is of SIMD type. So this represents a row major storage of the block vectors. And for this vector type, we then need a linear operator type that can represent the application to the matrix, since this is the main part of the Krylov methods. And this can be done by a matrix adapter. It turns a matrix into a linear operator. So how could this look? We have some loop SIMD type as a field type. Use this as the field type of a block vector. The matrix is defined as a sparse matrix. It's just a scalar matrix, since we use the same matrix for all stages, for all right-hand sides. And then we find a linear operator type that works on this matrix and the vector type. Before we see some results, take a look at a short performance analysis. So as I mentioned, the main ingredient of the Krylov method is the matrix vector product. For the block Krylov method, it's the block operator product. So if we look at the arithmetic intensity, the standard sparse matrix vector product has an arithmetic intensity of 1/8. And if you use the block operator using SIMD, this increases to k/4 k plus 1. If you look at this for k equals 16, this increases by around, so a factor of 1.8. On the right-hand side, you can see a small performance model, named the simplified execution cache memory model, where we assume that the time depends on the computation time, the memory time, and the register time. It's just the effective times, the maximum of those time. And what we measured is, we measured how long does it take to execute block operator product for k right-hand sides of block size of k. And we plot the time per column against the number of columns. And what we see for small k, this decreases. But for larger k, it increases slightly again. So we see a sweet spot at 8. And why does this increase? The reason for this is a single row of the block vector now occupies more space in the cache. So this might be the reason why this gets slower. We have another example, another benchmark, where we solved linear systems for 128 right-hand sides with a block CG and IMG preconditioner, and measured the times and counted iteration numbers, where we consider k right-hand sides in parallel. And what you can see is, the more parallel right-hand sides we choose, the less iterations are needed. Actually, this behaves quite optimal. Whenever we double the number of right-hand sides, the iteration count halves. But if we look at the times, the fastest we get is for k equals 16. And even though for larger k, we need fewer iterations, we don't get any faster because of the cache behavior. So another part is the pipelining we choose. So we use an exact Jacobian for the first stage and an inexact Jacobian for all other stages. So we make an additional linearization error. But due to the pipelining, what we get is we get improved initial guess for the next stages, since we do an exact Newton for the first stage, and when the exact Newton for the first stage runs, we for free get an approximate Newton iteration for the other stages. So this effect actually becomes even more prominent for later stages once the pipeline is full. And this results in less Newton and Krylov iterations needed per stage. So in an optimal case, it can happen that after every single Newton iterations, the stage gets shifted out. So each stage only needs one Newton iteration until it's shifted out. So this would be some optimal behavior. But clearly, this depends on the dynamic of the nonlinear operator. So the more the operator changes over time, the worse the approximation error gets that we make by choosing the wrong iteration. So let's take a look at some numerical experiments. In the first example, we tested for the nonlinear diffusion reaction equation. We choose Q1 finite elements in space and implicit Euler in time. And we simulated 40 time steps. And if you look at the iteration counts, you can see the more parallel time steps are considered, the less iterations are needed. And actually, if you look at the for 2 and 4 parallel time steps, the number of Newton behavior for the Newton iterations is nearly optimal. So we nearly half the iteration count. And if we go further, with further parallelization, don't get a benefit anymore. And the reason is we are in this behavior where page is shifted out up a single. If you look at the Krylov iterations, I can see we reduced the number of inner iterations by around 70–75%. But an important part is the solver time. So how long does the linear solver actually run? And we can see that the best results is gained for 4 parallel time steps, where we get a speed up of around 6. In another example, we looked at Richard's equation, which is an equation that models the flow of water in unsaturated soil. So we have some pressure head psi, water content theta, k. And this is a highly nonlinear problem. It's degenerate parabolic, and I've shown here the dependencies between theta and k just to see that this is actually quite nonlinear.
A little bit of powers there.
Yeah. So a problem with this equation is the Newton method might fail. So what we choose is we choose a different linearization, or a nonlinear iteration, namely the L scheme. I don't know if you know this, but it can be interpreted as a quasi-Newton method that makes use of the monotonicity of theta. So, and it only replaces the derivative by a constant L. So that's why we call it L scheme. If you look at the results, you get some similar results as before. The more parallelization we consider, the less iterations are needed. For 2 and 4, the behavior seems to be quite good. But for more parallel time steps, the benefit is only moderate, but probably because of the splitting error, the larger splitting error. If we look at the Krylov iterations, we get a reduction by about 80–85%. And for the solver time, you can see the fastest we get is for parallel time steps, where we get a speed up of 3.1. Come to a conclusion. What we presented is a generic framework for stiffly accurate Kutter methods based on some very basic parallel time ideas. We reformulated the system for the stages, the matrix equation for the multiple stages, and then use vectorized Krylov solvers to increase the arithmetic intensity and with the vectorization. Results show that we could reduce the linear solver time, factor of around 3, and the number of linear iterations was reduced by 70–85%. But all benefits we get are basically for free, since we gain these due to the vectorization. And due to its structure, it's applicable to a wide range of linear and nonlinear problems. So you can choose the linearization as you want, the discretization as you want. Just a small outlook. We want to analyze the splitting error, so maybe we can get a priori estimate for the performance, or how does the nonlinear operator affect the behavior. And instead of applying a splitting approach to achieve the desired structure for the matrix equation, we could think of a paradiac approach. We consider the space-time problem. We can transform this a little bit and then diagonalize time-stepping matrices. And now the operator in the center can be solved using Bloch-Krylov methods under a few assumptions. But the problem is time-stepping matrices will not be diagonalizable. So it might be a problem. So there's a preprint on archive if you want to take a look at this. Thank you.
So I love this presentation because I was thinking about something like this. What I'm going to present on Friday is a bit like this. Although I didn't finish, I just have the idea. So I will come to discuss with you. But I want to ask, in implementing the Newton's method, how do you handle the inverse
of
the Jacobian, of those Jacobian? Because if you want
Krylov method.
block,
The Krylov method.
thank you.
Yeah, thanks for the splitting node.
Yeah.
With a like block diagonal.
I can go back.
Right down there. You end up with a preconditioner that's essentially this one where you knock out. So your preconditioner is the block diagonal.
Yeah.
If you use that preconditioner for the non-vectorized one, flattened out, you don't see any residual drop until you've done NT iterations. Does compressing it into the matrix equation get over that? You start seeing a residual drop before you take an NT iterations. So that's really interesting.
I'll take a look at this. Can't answer this. Sorry.
Is the action of the matrix only propagates information?
Yeah.
And the inverse of the precondition. Or down at all. You NT iteration. Then if you have like the fully normal.
That depends on what you have in these blocks. That's an algebraic argument that's wrong if these blocks don't propagate anything. Just take a heat equation with Dirichlet boundary conditions and these blocks don't propagate.
In the preconditioner, sorry, or the
Yes, you just do the block inverse and you propagate much faster than block by block because these blocks don't propagate information. In a heat equation, everything is damped out. Algebraically, your argument is correct, but there are M blocks where the argument does not apply. That's something I showed last year in the pit.
Oh, well, it just depends on the local source term.
Exactly, it's only the local source terms that and everything else dies.
Yeah, and this is
so you can converge in 3 iterations if we have 300 blocks with this preconditioner, because everything else dies.
Yeah,
nothing is left in this iteration. This is really weird.
Yeah,
it does not work with Neumann conditions.
Yeah,
with Neumann conditions you have to propagate everything through.
There's a little paper from Andy Wathen from a while ago showing the NT iterations, but I think he's doing it for hyperbolic equations.
Yeah, it depends on what you have in these blocks. So. If you have Neumann condition already for a heat equation is dead, but the only propagation is a constant that you need. So it's very cheap. So algebraically, all is correct what you said.
Yeah, we did diffusion reaction, we did Richards, also tested for linear problem.
How do you achieve the higher arithmetic in the multigrid part? Is it just regular multigrid using a data structure?
Well, I actually don't know how the multigrid there works. So the solver doesn't this.
That's something you just plug in and
yeah.
Okay, I think we're ready to wrap up and investigate where this reception is.